Welcome to the deep dive. Today we're digging into really one of the big questions in AI right now. When you take a large language model and fine-tune it with reinforcement learning, RL, does that actually make it, smarter? Does it find new ways to reason?
Or is it maybe just getting better at finding answers it kind of already knew deep down from its pre-training?
Exactly. And this is a real point of discussion, isn't it? There's been research suggesting RL might hit a wall pretty fast.
Yeah, some studies definitely point towards limitations, maybe not adding truly new skills or performance even dropping off after a while. Maybe after just a few hundred training steps.
Right. But the paper we're diving into today, it really pushes back on that idea.
It does. It introduces this method they're calling prolonged reinforcement learning, ProRL for short. And the name kind of gives it away. The idea is training for much, much longer than people typically did.
Okay, so our mission here is to unpack what they found. We want to understand how ProRL actually works, look at the, frankly, pretty surprising results they got with their model Nemotron Research Reasoning Quinn 1.5b, and figure out what this all means for RL's potential to expand reasoning. Can it really unlock new stuff? Let's get into it.
Okay, so yeah, let's start with that core debate. Is RL actually building new reasoning pathways, new sort of mental tools, or is it just sharpening the model's ability to retrieve and use the knowledge it already got from that massive pre-training phase?
Yeah, like, is it learning to invent a hammer or just getting really good at finding the hammer that was already buried in the toolbox? Some earlier work seemed to lean towards that second idea, right? That RL helped use the existing tools better but didn't add new ones.
Exactly. Some studies observed that RL didn't seem to unlock capabilities the base model flat out didn't have, and sometimes performance on certain metrics even went down if you sampled broadly. But this paper suggests, well, maybe those conclusions came a bit too soon. They argue there might have been some limitations in how those earlier studies were set up.
Like what kind of limitations?
Well, two main things. First, maybe an overfocus on specific areas, like certain types of math problems where the models were already, really heavily trained.
Ah, okay. So if the model's already acing that specific thing, RL doesn't have much room to show off any new skills it might be learning elsewhere.
Precisely. It's not being challenged in the right way, perhaps. And the second, maybe even more important point they raise is stopping the RL training too early, like after only hundreds of steps. Their whole argument hinges on the idea that you need sustained, stable training over a much longer period to really see these novel reasoning strategies emerge.
Which leads us straight to ProRL, prolonged reinforcement learning.
Hmm.
What's the secret sauce here? What lets them train for, I think they said, more than 2,000 steps, effectively?
Right. It's not just about letting it run longer. You need specific techniques to keep it stable and learning. They highlight a few key components. First is KL divergence control.
Okay, what does that do?
So KL divergence is basically a way to measure how different the model's current strategy, its policy, is from some reference point. Using it as a regularizer stops the model from changing too drastically, too quickly. It helps keep things stable, but also preserves a bit of randomness or entropy, so it keeps exploring instead of just locking onto one single approach too soon.
Got it. Keeps it from getting too narrow-minded, basically.
Kind of, yeah. But the trick is, over really long training runs, that KL penalty itself can start to hold the model back too much. It can sort of stifle further improvement.
So how do they fix that?
That's the second key piece. Periodic reference policy resets. Every so often, they essentially update that reference point to be closer to the model's current abilities, and they reset the optimizer state too.
Ah, like moving the goalposts based on progress.
Exactly. It gives the training a kind of refresh, letting it continue to improve and diverge from the original base model without that KL term stopping it cold. It's a clever way to balance the stability with allowing for significant continued learning.
Makes sense. And they didn't just train it on math problems, did they? The task diversity seems important.
Hugely important. That's the third pillar. They used a really broad set of tasks, about 136,000 problems across math, coding, STEM, logical puzzles, and just general instruction following. The idea is that this wide exposure is crucial for learning reasoning skills that actually generalize, rather than just tricks for one specific domain.
Right, learning principles, not just answers. They also mentioned using things like decoupled clipping and dynamic sampling.
Yeah, those are techniques borrowed from other recent work, like DAPO. Decoupled clipping helps encourage exploration by setting different limits on how much the model can increase versus decrease the probability of certain outputs. And dynamic sampling is smart. It focuses the training on the just right problems. It filters out the ones the model finds trivially easy or impossibly hard, concentrating effort, where there's actually something useful to learn from the reward signal.
So it avoids wasting time on problems that are already solved or totally out of reach at that moment.
Exactly. Both help fight against entropy collapse, which is a common issue where the model just becomes too predictable and stops exploring new possibilities, especially during long training runs.
Okay, so a pretty sophisticated setup,
hmm
and they use this ProRL approach to train their model, Nemotron Research Reasoning Quinn 1.5b. How did it actually perform?
Right. So the model itself, it's a 1.5 billion parameter model, which, isn't tiny, but it's certainly not one of the giants out there today. They call it a generalist model. But the performance, well, it's pretty remarkable.
Or keep us in suspense.
Okay. So across their big evaluation suite, this 1.5B model consistently and significantly beats its own base model, the version before ProRL training. No huge shock there, maybe.
Right, you'd hope the training helps.
But here's the kicker. It often matches or even beats the performance of DeepSeek R17B.
Wait, the 7 billion parameter model, so more than 4 times bigger?
Yep. On many tasks, this much smaller model, trained with ProRL, is performing as well as or better than a model over 4 times its size.
Wow. Okay, that is genuinely surprising. That implies the training method itself is incredibly effective. Huge implications there for efficiency and accessibility. What were some of the specific gains?
The numbers are pretty impressive. Looking at Pass at 1, that's getting the answer right on the first try, the average improvements were big across the board. Like math was up about 14.7%, coding saw a 13.9% lift, STEM reasoning jumped 25.1%, instruction following up 18.1%.
And I heard logic puzzles saw a really dramatic increase.
Oh yeah. Logic puzzles' average Pass at 1 improvement was a massive 54.8%.
5%.
Almost. It really suggests ProRL is making a huge difference in those areas needing complex, maybe multi-step reasoning, where the base model likely just wasn't cutting it. And crucially, they show performance, both Pass at 1 and Pass at 16, continuing to climb steadily even after 2,000 training steps. This directly counters that old idea that RL just plateaus really early.
That massive jump in logic, especially,
Yeah.
that feels like more than just optimizing existing knowledge. Did they find any direct evidence that ProRL is helping the model find genuinely new ways to solve problems?
Yes, and this is probably the most exciting part of the paper, suggesting RL really can expand the model's core capabilities. They used a metric called the creativity index.
Creativity index, how does that work?
It basically measures how novel or unusual the model's generated solution path is compared to typical examples found in its massive pre-training data.
Okay, so a higher score means the solution looks less like the common stuff it already saw, more original.
Exactly. And their results show that as ProRL training progresses, the model generates solutions with a higher creativity index. This strongly suggests it is finding and using new patterns, new ways of thinking that weren't just the obvious or frequent ones it learned initially.
That's compelling. And wasn't there something really stark about problems the base model just couldn't solve at all?
This is maybe the killer evidence.
Hmm.
The paper points out, and you can see the implication in their figures, that the ProRL model achieves 100% success on many tasks where the base model fails to produce any correct solutions, regardless of the amount of sampling.
Hold on, say that again. The original model, you could ask it 1,000,000 times, and it never got it right.
0% success for the base model on those specific tasks.
And the ProRL model.
100% success. Solve them every time.
Wow, okay. That's about as clear evidence as you can get that something fundamentally new has been learned.
Okay.
Right? It's not just accessing known stuff better. It's finding pathways that were literally impossible for the base model to find. It must be constructing new reasoning chains somehow.
It really points towards RL, given enough time and the right conditions, being able to explore and build capabilities that just weren't there before.
That's a game changer for how we think about RL's role. But it wasn't like ProRL magically fixed everything equally, was it? The paper mentioned some nuance there.
That's right. It's not a universal silver bullet. A key finding is that ProRL seems to help most dramatically in areas where the base model was initially weakest. There is a clear inverse relationship. The lower the base model starting score on a task, the bigger the improvement from ProRL.
So it's not necessarily about making A+ tasks into A++ tasks, but more about turning F's and D's into A's and B's. It lifts the floor significantly.
That's a great way to put it. It's most transformative where the capability gap was largest. They actually broke down how performance evolved during training into 3 main patterns or regimes.
Okay, what are those?
First is diminish. These are tasks where the base model was already pretty good high pass at 128, meaning it could find a correct answer if you gave it lots of tries. Here, ProRL did improve pass at 1, made it more confident on the first try, but pass at 128 actually went down.
Huh. So it got more precise with its top answer, but maybe lost some ability to generate diverse correct solutions, like sharpening the point of the pencil but losing some breath.
That's a good analogy. It seems to focus the probability mass on the best known strategies, possibly at the cost of exploring alternatives. They saw this often in math domains where the base model was already strong.
Interesting. What's the second pattern?
Plateau. For these tasks, they saw good gains early on in RL, both in first try success and overall ability. Pass at 1 and pass at 128 went up, but then it just leveled off. More training didn't really add much more benefit, performance saturated.
Okay, so early gains, then stability. And the third one must be where ProRL really lives up to its name.
Exactly. Sustained. These were often the more complex tasks, like coding and those tricky logic puzzles. Here, performance just kept climbing and climbing with prolonged training. Pass at 1 and pass at 128 both continued to improve significantly over the extended training period. This is where the prolonged aspect is absolutely critical for unlocking those deeper reasoning capabilities.
That breakdown is really helpful. It shows ProRL isn't just one thing. Its impact depends on the starting point. It's most powerful where it's most needed. Okay, so beyond the specific training tasks, did they show this improved reasoning generalizes? Can it handle completely new problems?
Yes, and that's crucial, right? Generalization is key to showing it learned abstract principles. They tested this in 2 main ways: out of distribution, ode tasks, and tasks with increased difficulty.
How to do on Ode?
Pretty well. They used tasks from a benchmark called Reasoning Gym. One example they highlight is BoxNet. The base model was completely unable to solve it, 0% success no matter how many tries.
Could do it, period.
Nope. But the ProRL model could. And importantly, comparing the model partway through training versus the final fully trained version showed that the extended training really solidified and amplified that ability across the board. It wasn't a fluke. The long training built a genuine, stable capability on this totally unseen task type.
That's strong evidence for learning something transferable. What about increased difficulty?
They looked at a graph coloring task. They trained it on graphs with, say, 10 nodes, but then tested it on graphs with more nodes, which gets exponentially harder.
Right, complexity increases.
And predictably, performance drops for all models as the graphs get bigger. But the key thing is, the model trained with prolonged RL maintained significantly higher accuracy across all the larger graph sizes compared to the base model or the one trained for less time.
So even though it got harder for everyone, the ProRL model handled the scaling complexity much better. That really sounds like it learned a more robust fundamental approach.
Exactly. It suggests a deeper understanding that isn't just tied to the specific complexity level it saw during training.
The training itself sounds like quite an involved process, with those resets and stages you mentioned.
Oh yeah, it's not trivial to pull off stable training for thousands of steps. They have an appendix detailing the multi-stage recipe. The key takeaway seems to be that those periodic hard resets of the reference policy and the optimizer are vital, not just for stability, but also for allowing the model's policy to gradually drift further away from the initial base model, which is necessary to find those truly novel solutions.
So the resets are strategic, not just hitting refresh.
Right. And interestingly, they noted that just generating longer answers wasn't always the reason for better performance, kind of pushing back against the simple idea that the model is just thinking harder by being more verbose.
Got it. So ProRL looks really promising for boosting reasoning, especially in smaller models. But what are the catches? What limitations did the authors themselves point out?
Good question. They're quite upfront in the appendix. The big one is compute cost. This kind of prolonged training, especially generating and evaluating potentially long reasoning steps, takes a lot of computational power.
Right. The very thing that makes it work, the long training, makes it expensive.
Exactly. That could be a barrier for some researchers or smaller teams. There's also a question mark over how well this exact recipe scales up to models that are, vastly larger than 1.5 billion parameters. The complexity of the training process itself with the resets needs careful handling to ensure it works reliably. And finally, while their training data was diverse, it's still just a sample of all possible reasoning tasks. So you can't guarantee these gains would appear for absolutely any new type of problem.
Those are important practical points. What about the bigger picture? The societal impact of potentially creating models with significantly enhanced reasoning.
They discuss this too, both the upsides and the significant challenges. On the plus side, there's the potential for, well, maybe even superhuman reasoning on some tasks. But maybe more immediately impactful is the democratization aspect. Making small models perform like much larger ones lowers costs, reduces energy needs, and makes powerful AI more feasible for on-device or on-premises use where data privacy is critical.
That's a huge benefit, making advanced AI more widely accessible and deployable.
Definitely. You can imagine applications in science, healthcare, education, like really smart AI teaching assistants. But the flip side needs serious attention.
Like the compute costs creating a divide.
Yes, potentially widening the gap between those with resources and those without. But also, more fundamentally, enhanced reasoning power brings risks of misuse. If a model suddenly becomes capable of complex planning or problem solving it couldn't do before, that needs careful oversight. The paper stresses the need for ongoing monitoring as capabilities emerge.
You need to know what the model can suddenly do.
Precisely. And they emphasize that this kind of capability enhancement must go hand in hand with robust value alignment techniques. We need to ensure these more powerful models are aligned with human values and goals. Plus, we need better ways to evaluate them, dynamic benchmarks that evolve as the models themselves do.
So pulling it all together, what's the main takeaway from this deep dive?
I think the core message is that this paper provides really compelling evidence that we might have underestimated RL's potential for expanding reasoning. It shows that with the right techniques, stability, diversity, and crucially time-extended RL training like ProRL can help models develop genuinely novel reasoning patterns beyond what the base model could access. And these gains can generalize.
So it really challenges that earlier view that RL just polishes what's already there. It suggests it can actually build new capabilities.
Yeah, it significantly shifts the perspective. Sufficient, well-managed training time seems to unlock surprising potential.
Okay, so for you, the listener, trying to keep up with all this, what's the bottom line? Well, it means don't count out smaller models. This research suggests that smart training, like ProRL, could make models with, say, 1.5 billion parameters surprisingly powerful, maybe even rivaling much larger ones on complex reasoning tasks. That could make advanced AI much more practical and widespread.
And remember the nuance. It's not magic everywhere. It didn't drastically improve tasks the model already aced, but it seems to be incredibly effective exactly where you'd want it to be. On the harder problems, the areas where the base model was really struggling or completely failing.
It's that ability to go from 0 to 100 on previously impossible tasks that really sticks with you.
It really makes you think about how learning can fundamentally change what's possible for these systems.
Which leaves us with a final thought. If this kind of prolonged reinforcement learning can unlock reasoning abilities that were totally absent before, enabling models to solve problems they've never encountered, well, what other completely unexpected capabilities might emerge as we continue to refine these training methods? What new doors could AI learn to build and open all on its own? Something to ponder.